We are now going to study a topic about systems of linear equations. So the first section we are going to do is called What is a System of Linear Equations? We have 3 learning targets for this for this topic. And in this section, the 3 learning targets are identifying what a system of equations is, identifying if a given point is a solution to a system, and writing a system of equations given a real-world situation. So I will repeat those again, and you need to copy this down into your notes. So again, the 3 learning targets for section 6.1 are identifying what a system of equations is, identifying if a given point is a solution to a system, and writing a system of equations that represents a real-world situation. So you got some handouts that you need to cut up and paste into your notes. So go ahead and, if you haven't yet, pause this and cut along the dotted lines, and we are going to paste in as we take notes. So when you're ready, go ahead and start this, and we are going to start with the 2 runners run a 40-yard dash at speeds shown in the diagram. So runner 1 starts 4 seconds before runner 2. So make sure that you look at the words. Runner 1 starts 4 seconds before runner 2 to make the race more competitive. Will runner 2 pass runner 1? So here, runner 2 is running 8 yards per second, and here it says that runner 1 is running 4 yards per second. But runner 1 has a 4-second head start. So if you think about the 4-second head start with 4 yards per second, that means that runner 1 will have run 16 yards already before runner 2 starts. Let's go ahead and write that down. So runner 1 ran 16 yards before runner 2 starts. So that means if he ran 16 yards and it says that they have to go 40 yards in the race, runner 1 has to go 24 more yards. So runner 1 has to go 24 more yards. So think about how long it will take runner 1, who travels at 4 yards per second, to go 24 more yards. And if you're thinking correctly, you should come up with 6 seconds. So runner 1 will take 6 seconds to finish the race once runner 2 starts. Now let's think about how long it takes for runner 2 to run, and he has to run the entire 40 yards, and he runs 8 yards per second. So runner 2 will take 5 seconds to run that 40-yard dash. So since it takes him less time, the answer to the question, will runner 2 pass runner 1, is yes. And I know that because it takes runner 2 5 seconds and it takes runner 1 6 seconds after he got the head start. Alright, now we have a new scenario. Suppose runner 1 gets a 3-second head start. We are asked to create a table using this information. Alright, so at time 0, we're going to use colors here. So if you have the ability to grab colors, that would be good. If not, you can just use your pencil. but I'm going to put runner 1 in red, and at time 0, runner 1 has not run anything. Runner 1 gets the head start, so as soon as time starts, he starts running. So 1 second he will have run 4 yards, and this is based on this information here. After 2 seconds he will have gone 8 yards, 3 seconds is 12 yards, 4 seconds is 16 yards, and 5 seconds is 20 yards. So that is the pace that runner 1 is running. Let's use green for runner 2, and he has to wait 3 seconds before starting. So at 0 he's gone 0, at 1 he's gone 0, at 2 seconds he's gone 0, and at 3 seconds he's gone 0. Once 3 seconds is passed, he starts running, and he runs 8 yards per second. So on the 4th second he has run 8 yards, and on the 5th second he has run 16 yards. So there's our table for this information. And now we're going to come down here and put that information in the graph that you see, and we have to come up with equations for those runners. So I'm going to go back to runner 1, and I am going to plot points on my graph. So before I do that, let's go ahead and put some labels on the graph and some scales. So the y-axis, it says y is distance, and distance is in yards. So I'm just going to put yards here. And the x value is time, and time is measured in seconds. So I'm going to put seconds here. And if you look at the seconds, they're going up by increments of 1. So when I do my scale, I'm just going to mark every tick as 1 second. Now notice that I didn't have to put every single number down. I'm just putting some tick marks down and putting what number is for each several of them. And then the yards, we're traveling 40 yards in the race. So there are 20 tick marks here. So I'm going to make the top one be the finish line at 40 yards, which means each tick mark here is 2. So that means 10 is here, and that's 20 yards. And that's 30 yards. And then I'm up to 40 yards there. So now let's plot the points for runner 1. At time 0, he goes 0. 1 second, he traveled 4. 2 is 8. 3 is 12. 4 is 16. And 5 is 20. So if I continue the race until he gets to the finish line, I would just continue those points all the way up to 40 yards. Alright, and he is moving continuously, so I'm going to go ahead and connect the dots. So that is the line for runner 1. Now, runner 2 is a little different. He has not traveled for the first 3 seconds, so at 3 seconds he is still at 0, so I'm going to put that point there. And then at 4 seconds he's gone 8 yards. At 5 seconds he's gone 16 yards. And then if I continue that pattern, I will continue up 8 yards every second. And I will have that graph. So let's go ahead and connect those dots. Okay, so that represents the scenario. And now we're asked to write equations of the lines that we just drew. So if you look at runner 1, the orange line or red line, that is a direct proportional relationship. So we know that y equals mx is our proportional relationship. And the m is the slope or the rate that he's traveling. So he's traveling at 4 yards per second. So the equation is y equals 4x. Now with runner 2, he is not traveling in a direct proportional because it does not go through the origin. So we have y equals mx plus b for this one. M is the slope or the rate he is traveling, and he's traveling 8 yards per second. So it's y equals 8x, but now we have to figure out what the y-intercept would be. Now if you look at the line, you know that it's going to eventually hit the y-axis in the negative values. So you have to think, how far would he have had to travel in 3 seconds to get to this 0 where he's starting? So in 3 seconds that he didn't travel, he would have gone 24 yards. So that means that the y-intercept is going to be down at negative 24. And that's the equation for runner 2. What we have just worked with is a system of linear equations. So you can see on the graph that we have 2 lines, and a system has to have 2 or more equations with it, which is what we have right here. This is 2 equations. And it's a system of linear equations because they form lines. Let's take a look at this point here and talk about what it represents. So in this case, we're talking about 2 runners. Runner 1 is the orange and runner 2 is the green. Runner 1 and runner 2, those lines intersect at the values 6, 24. So the values 6, 24 are where they intersect. And that means that after 6 seconds from runner 1 starting, he has traveled 24 yards, and that is where runner 2 meets up with him. So it takes 6 seconds from the start of the race for runner 2 to catch up to runner 1, and they have both traveled 24 yards when that happens. So now let's go into some important vocabulary. So pause your computer and get these words written down, and once you have those down, we will put some definitions in. So pause if you need to. We are going to talk about what a system of linear equations is, and I just explained that on the previous slide. A system of linear equations is 2 or more equations that form lines when you graph them. A solution to a system is a point x comma y whose x value and y value make all equations in the system true. and we will go through examples of what that means. And the solution represents the point where the lines intersect. And you saw that on the previous slide where the two runners' lines intersect. That was the solution to the system. So let's see some examples, and this goes back to your cutouts. Your first cutout just has examples of systems and non-systems. So the three in the brown are systems of equations. They all have two equations in them, and when you graph them, they would be lines. In the purple, these are all examples that are not systems of equations. All of them are not because they only have one. And remember, a system requires two or more. Requires two or more equations. So each of these only has one equation, so that's why they are not systems. But another point is that these two right here, they are not even equations. They don't have equal signs. So make sure that when you're working with a system of equations, you have to have equal signs. So this doesn't have an equal sign, so it can't be a system of equations. All right, next we have an example where we're asked, is 2, 4 a solution to each of the systems below? And explain your reasoning. So what you need to do is you need to think when you plug x equals 2 and y equals 4, into each equation, is it true? That's what you should think. So let's talk about A. When you plug x equaling 2 and y equaling 4 into this equation, you would end up with 4 equals 2 times 2. And we all know that 4 equals 4 is correct. When you plug it into this one, when y equals 4, so we're going to have 4 equals 6 times the x value, which we're saying is 2, minus 8. Does that work? So does 4 equal 12 minus 8? Oops. And 12 minus 8 is 4, so yes, it works. So is this a solution? Yes, because, and remember when it says to explain, you use words. Yes, because 2, 4 works in both equations. All right, let's try part B. Part B, if we plug in 2 for x and 4 for y, does it work? So 2 minus 4 is negative 2. Does that equal negative 1? No. So the answer, I don't even have to check the second one. Okay. It may or may not work in the second one, but we don't have to check it. The reason being, if it doesn't work in both, it's not a solution. So no, because 2, 4 does not work in both equations. All right. We have one more example to do, and that is setting up a system when we are given a real-world situation. So in this example, wildlife biologists studied the weights of 2 alligators over a period of 12 months. The initial weight and growth rate of each alligator are shown in the table. We are asked to write a system of equations the biologists could use to compare the weights of the alligators. So let's refer back to material that we've learned in the past. When we see the word rate, we need to think of slope. The rate is the slope. So that when we have the equation y equals mx plus b, you need to know that the slope is the m value. So we have a slope of 1.5 and a slope of 1, and those are 2 separate equations. When we see initial, that means beginning, and the beginning value is our y-intercept, and that is the b value. So that makes it really easy to write our system. So if we talk about alligator 1 in red, alligator 1 has the equation y equals the rate, which is 1.5, x plus the initial weight, which is our b value of 4. So that's the equation for alligator 1. And let's do alligator 2 in blue. So alligator 2, we have y equals the rate, which is 1, x plus the initial weight, which is 6. So that is your equation for alligator 2. And then the way we show that it's a system is we put a little bracket between the two. So there is your system of linear equations. And now it's time for you to go to Google Forms, and here is the address you need. Now, this is not a hyperlink, so you can't just click on this. You either have to highlight and paste it into your URL, or you need to type it in as you see it, and it will take you to a Google form that you fill out and show me that you understand what you learned today. Have a great day.